AI. And I want to start off, first of all, by thanking everyone for joining. And second of all, by asking the commonly shared question, can you see my screen?
Yes, we can.
Yes, excellent. That's not the only cliche we're going to have today. But yeah, first of all, thank you everyone for joining. So a little bit more about myself. I'm part of Accenture. I sit in a company called Medano, which was acquired about 4 or 5 years ago, I believe. I joined post-acquisition. Um, I've got this part here, I call it the blurb. So I'm a data scientist. I'm also a chartered accountant. Um, Ross is a data scientist, a history of technical implementations of LLMs at scale, blah, blah, blah. Basically, I work mostly, I started off my career in audit. I realized after 1 year I really didn't like it, but I did get the chance to transfer into data analytics. I did that for 2 years. I finished my chartered accountancy. I got offered the chance to do a data science master's, and at the time, all I heard was, "Oh, 1 day off every week for 2.5 years, full pay." Yes, not realizing that it was actually quite a lot of work, but I fell in love with it. And at the end of that, it became a choice of where do I go? And I was in audit. It's very retrospective. If you think about data science, all of the cool stuff is prescriptive, predictive, forward-looking, generative now. So I kind of made the next decision, which was to move to Accenture. And I've done a variety of things. I've actually spent the last year and a bit in Accenture's customer engagement team. It's where we build customer engagement solutions, as you can imagine. And a lot of that is LLM at scale. So when I say at scale, I really mean we say accurate. We know it's accurate because it's measurable, because we've built pipelines, because it's done as part of our deployment process. So how do you make it something that is fundamentally scalable? I've also done a lot of training. So most of the UK's Gen AI analyst population, I'm one of the trainers. There are quite a few of us. As well as that, I've done various things to software engineers. I've trained software engineers on how to build prompts, how to build prompts into their workflows. I've also just finished a hackathon with quite a lot of the teams there. I think there was about 300 people across 50 teams, and some of the stuff that came out was really, really innovative. A lot of it, my current role focuses on software engineering, mostly because that is where LLMs at scale come in. But we'll get into that a little bit later on. Final bit about me, personal research interests, real-time audio and video streaming, verbal dialogue, voice to voice, low latency, which OpenAI have cracked very recently, it seems, with GPT 4.0, and also natural dialogues with those LLM-driven AI agents. So that's my sort of about me. But I don't want to talk too much about me because I'm here to kind of talk to all of you, and I'm here to talk to you about what LLMs actually are. I've got this thing, I've called it the foundation of knowledge. So we're going to start, as we were saying, it like sort of building up a picture. We're going to take a bit of a deep dive into it, but we're going to do it in a paced way. We're going to start off with some thought experiments, and then we're going to build up on top of them. There is a bit more content as well. We're going to talk about LLMs at scale. We're going to hopefully maybe even get onto image models, but I want to just start off by grounding us all on what a large language model actually is. And remember, LLMs are a type of generative AI, which itself is a subset of machine learning. So, how do LLMs work? Well, you might have heard people say they just predict the next word. And I mean, they're not wrong. There's some caveats to that, and we'll come back to that and we'll expand on that description. But what do they mean by that? Like, what is predicting the next word when we actually look at, well, how it works? And I'll tell you how it is. What we do. So look at this sentence here. The quick brown fox jumps over the lazy dog. For anyone that knows anything about fonts, this is the sentence that fonts use to illustrate it because it contains every single letter of the alphabet. When you give an input to a large language model, you're giving a prompt. That's what we talk about when we mean. So you give it an input, and it will predict the output, and the output is a set of generated text. However, the way it does that is like this. So our input prompt is the quick brown. It predicts the word fox is coming next. It then takes that and it goes the quick brown fox, and it predicts the word jumps. And then it takes the quick brown fox, jumps, and it predicts over. And it continues doing that until it reaches the end of a sensible generation. There might be some people in the audience that are saying, but it's not words, it's tokens. You're right, but we'll come back to that. So this is the basics of how they work. But what does that actually mean? Like, let's go a bit deeper. So we're going to start off by talking about the concept of it. We're then going to talk about words as numbers. We're then going to do statistics on word numbers, then learning in a finite world, and then learning in a near infinite world. Now, don't worry, if you have no idea what any of this means except concept, that's fine. That's where we're going to start, and we're going to gradually build up into the rest of the pyramid. So So starting off at the top. Well, we know they predict the next word now, don't we? So if I ask somebody to finish this sentence, to be, comma, or, most of you would probably say to be or not to be. Some of you might even know the full quote. To be or not to be, that's the question. And you're right. It is the answer. Why is this though? Well, if we think about that input, to be, comma, or, it's grammatically incorrect. It's Old English. It's not used in a daily basis or even regularly anywhere. But if you have seen that, it's probably in the context of Shakespeare, one of the most famous playwrights, one of his most famous quotes. We've all sat down in maths class and thought, oh, I don't know how to answer question 2b. You know what I'm going to do? I'm going to be really funny. And you write that down and you think you make the teacher laugh, you'll get a mark. You haven't. They've seen it all before, 100 times. So from a statistical angle, if we think about what we have here, we've got low occurrence of the input, to be, comma, or, and high prevalence. If you have seen to be or, it's probably in the context of that quote, to be or not to be, that is the question. So from a statistical angle, to be, comma, or doesn't really happen. And the completion of not to be, that is the question, is probably what you have seen. Now let's flip it on its head. Finish this sentence. To be. You probably have an answer. You're not confident. You're likely wrong. The answer is to be continued if you're interested. But why can't we predict this like we could the previous one? Well, all we've done is add a comma and then or. And the reason is, to be is one of the most common phrases in the English language. There are so many ways to finish that sentence that we would just not be confident in an answer. We don't know the statistical answer, so we don't feel comfortable giving it. But what if you could be? What if you could understand and predict what the next word will be? And for those people that know about tokens, like I said, don't worry, we will get back to that. So you don't know the correct answer, and if you do, it's because you guessed well. To be continued as the answer. There is an interesting part of some large language models, because a lot of the training data is scraped from the web. Some of them have it where it's to be successful is also a completion, and that comes from a lot of sort of the internet self-help articles about running a business and such. So that is one interesting tidbit. Okay, so we know we need to do statistics on words, but we can't do statistics on words. Statistics are something you do on numbers. Words are not numbers. So what we need to do is we need to be able to turn words into numbers. So this is what's called an embedding or a vector. You might have heard it referred to. It's a series of coordinates. There is an argument whether it's a series of coordinates or a series of directions, but it doesn't really matter how you think of it. Coordinates is easier to hold in your head. This is the embedding for the word king. The way that we read this, so this is a graphical representation. That first light orange bar, if you look at the first number, it's 0.50451. That's between 0 and 0.8, so it's light orange, and you can read along the rest of the array for that. The other thing to point out, this is a very, very small embedding. Most of them are 356 at a minimum, 1,536 dimensions, so a lot of numbers, but I wasn't going to put that up on a slide because we're not here to read those. You don't need to understand these numbers. No one does really. That's the point. But the way that these embedding models are trained is based on reading vast amounts of text. So you should note that this is a pre-step to all the LLM stuff, turning words into these vectors. But in order to actually come up with the system to do that, the way it works is when you look at words and how close they are together. If I said to somebody, I want to book a cafe, and my friend says, I want to book a restaurant, those are basically the same thing, aren't they? Cafe, restaurant, place to eat, whatever. But you would never say, I want to book a cafe restaurant. You might, but people aren't going to say that really. And what happens is you look at how close words are together across your whole data set. If you took a book and you looked at the first and the last word of the book, and I asked you to tell me how relevant they are, you'd probably say, not very. You're right. If you looked at the first and last word of a chapter, you'd still say they're not very related, but probably more than first and last of the book. Paragraph, sentence, and then finally two words right next to each other, very, very relevant. And that's why something like restaurant and something like cafe in this coordinate system would be right next to each other because they'd be surrounded by words like booking, friends, eating, having a meal, different types of food and such. So that's how we build up these models. And it lets us do some really interesting stuff. Every data scientist in the world, I think, has heard this example. King minus man plus woman equals queen. But let's look at it for a second. I do just want to remind you, please feel free to add questions as we go in the Q&A function. If I think it's something that's going to come up, I'll weave it into our answers, and we've also got time at the end to kind of have that discussion. So back to this. King minus man plus woman equals queen. This isn't something you've been taught. No one has sat down in maths or English and told you that this is how that you figure out this equation, but it kind of makes sense intrinsically. King, male royalty, take away masculinity, add femininity, you get female royalty, queen. So those are the embeddings for king, man, woman. That's king minus man plus woman. It's very easy maths, by the way. All you do is you take the first value for king, you deduct the value for man, you add the value for woman, and that gives you the number in the first position. And you do that for all the numbers in all the positions. And that's the one for queen. Now, they're not the same. I will give you that. There's two things I want you to know. One, being exactly the same doesn't matter, and I'll explain why in a second. And two, this is a very, very small embedding dimensionality. So usually it would run much, much longer, and there's much more data points to sort of compare. But this is pretty cool. Now we can do maths on words. So remember, we needed to do statistics on words. We've now turned words into numbers. So the next stage is statistics on words. Think about your vector maths if you think back to high school. Ignore everything we've just said. If I gave you the direction and magnitude, distance that is, of a vector from my house to my office, and then I gave you the same, a magnitude and direction from the office to the gym, you could do the calculation to figure out how to get from my house to the gym, just based off those sets of coordinates. This is pretty interesting because if you think about that, if my office and my gym are right next to each other, then the directions from my house will be pretty much the same, won't they? I mean, not exactly, but similar enough that you could find your way to one or the other. And when you calculate the combined vector, it's just going to be the middle of the two. The same thing happens if it's equal and opposite, other ends of town. And this is how we can take the vectors for king minus man plus woman and the vector for queen, and we can determine that they are similar enough. This is called cosine similarity. It's a well-used technique. It's got its upsides, it's got its downsides, but it's one of the main ways of enabling LLMs at scale, but we'll come on to that much, much later. This lets us do some pretty good stuff. If you look at this, so this is airline intents data. If you look at that cluster in the top right, so we've crushed this down to 2 dimensions. So obviously we've lost some data points there as well. Bear that in mind. But these are quite closely grouped together. And if you look at them, what ground transportation is available in Boston up in the top right there? Show me a list of ground transportation at Boston Airport. Show me Boston ground transportation. All of these are quite close together. They've got the same stuff, ground transportation, Boston, a little bit further apart, but in general, that's a group. If you look down in the bottom left, I like the lowest fare from Denver to Pittsburgh. And then if you go up, show me round trip first class tickets from New York to Miami. It's pretty safe to say that yes, they are the same group, but the reason they're further apart is because they're kind of different. One's round trip first class, the other's lowest fare. It's different size, but they're close together, but not as close as all the ground transportation ones. One of the most interesting things that we've done in production is actually deploying traditional clustering techniques alongside LLM summarization. The theory is you get an LLM to get the text really short, and then you do stuff like this. We'll come on to that later, but it's quite a cool one. So anyways, just to recap, we've made it to level 3. The next 2 levels are all about how they learn, but we knew that we needed to be able to predict the next word from a statistical angle. We know that we can turn words into sets of coordinates using embedding models, as we went through on the 2nd level. And now we know we can do statistics on those words using some basic high school maths. It is a little bit more complicated when you have like big arrays of vectors, but that's why we have computers. We don't have to do multi-dimensional calculations. We just get the computer to do it for us really quickly. Okay, but how do they learn? I want you to forget everything we have just talked about in terms of the entire English language or the entire set of documents for any language. And I want you to look at this. We are going to train a transformer, which is the technology that sits underneath all of these models, on a finite length Markov chain with context length of 3. I'll give you a secret about some data scientists. We like to use big words. All that means is a binary string. What this is, it's 1, 1, 1, 1, 4 ones, and then a 0, repeating 3 times. We are going to train a transformer on this. Its entire world is 1, 1, 1, 1, 0, repeating 3 times. Doesn't know anything about the English language or anything, and if you think about it, there's only 2 options when it tries to predict what comes next, 1 or 0. So what does context length of 3 mean? Well, this is how we train it. What that means is we start by looking at the first 3 ones. And then it looks at what comes next. So it sees 3 ones in a row, and it says, right, if I see 3 ones in a row, I'm going to see another 1 100% of the time. We then slide that window along now. We see 3 ones again. But this time it sees a 0. So it says, okay, if I see 3 ones in a row, 50-50, 1 or 0. And we do that for the full chain. We go around the full cycle of training data. It's called an epoch every time you go around the training set. If we did this for 50 epochs, we end up with a very scary looking graph like this. Don't get lost in the detail. Follow me. The way we read this graph, so you see the triple one and it loops back on itself. The way to read it is the thing that it's taking you to. So that 1 is telling you that the next thing that you're trying to predict in the sequence is a 1. So obviously, when you drop the first digit there and you add a 1 on the end, you still end up with triple one. When you drop the first digit and you add a 0 on the end, you end up with 110 down there. The astute among you will notice that that is 55 and 45%, not 50-50. I didn't lie to you, but there is a little bit of randomness in how these models are trained. If we train this for a larger number of epochs, 500, 5,000, infinite, you would expect that to tend towards 50-50. Okay, what about down here? 000. We didn't see this in our training data set at all. It doesn't exist as far as our Markov chain transformer is concerned. But if you think about it for a second, there's only really 2 options that it can be. And if both answers are just as unlikely as each other, then both answers are just as likely as each other. So it's 50-50, 1 or 0. This is actually how you see the emerging capability of generative AI models to deal with data that they haven't seen before, how they can generate apparently new data, and it's because of this particular phenomenon. The other thing to point out is when you do expand this to the full English language, there's never really such a thing as everything being just as unlikely. There's always something that's a little bit likely. So if you've stuck with me now, we're almost there. We know that they predict the next word. We know that we have to do statistics on those words. But in order to do that, we need to turn them to numbers. We now know how to do statistics on numbers, which are representing words. So we can do all that. And we now know a little bit about how they train, but we only know that in the context of how the, like this Markov chain. I mean, it's different when you're trying to predict words. And you're right. And that's why we don't predict words. We predict what's called a token. You might have heard of a thing called a tokenizer. They usually go alongside any kind of language model, really. What a tokenizer does is it breaks up words. Now, sometimes the token might be a word. Like if you read on the right on that picture, this is the GPT tokenizer. Down in the bottom right, you'll see that characters is all one highlighted part, and that is one token. Same with roughly are tokens. But then if you go to the very first part of the input, G, and then PT, and then dash, and then 3, those are all their own tokens. The general rule is it's about 4 characters in a token, but if you want to get a true cost of or a true estimate of tokens, you need to actually run the text that you're looking at through. And actually, a lot of these API-driven services, they charge you based on how many tokens you use. So the key thing here is when we're predicting what comes next, we're not predicting a word, we're predicting a token. I know I used word as an example for throughout all of the last 4 stages, but the reason we've done that is because I didn't want to throw too much information at you before we got to this step. So they are functionally the same though. It's just predicting what comes next. And actually it's kind of nice. A tokenizer is basically a big map of the tokens against a number. So roughly there, might be token 1,283,056. And then characters might be token 16, something like that. And it takes the text and it breaks it down into tokens. So a lot of when we talk about LLMs, there's a big step called pre-training. This is learning in a near infinite world. Don't worry too much about these slides. If you don't really get it in this part, it's okay. Actually, we'll show you the main part in the next slide after this. But to be honest, if we're at that level, if we're thinking comfortably with this, we're data scientists already. So the first stage in the development of LLMs, obviously you take internet scale data sets and you tokenize those inputs. And there's a bit of pre-processing. You've got your usual NLP techniques. So you'll take the word running and you'll stem it and you'll make it the word run, for instance. But the key point is you're building up all of these tokens. The only other thing is you do introduce some as well. You can see there in row 1, row 2, row 3, you've got end of text. Each model has its own way of representing these tokens, but usually there's like a special token that says this is the end of that. And that's how they know when to stop generating. They see, or they generate rather, an end of text token, and that is their stop word. I'm going to go on to the next slide. So do you remember how, if we just look at these colored bits, if you remember how we did the quick brown fox, this is basically the same thing. So in order to predict the green input, 3188, and 3188 will map to a specific token, and so do all these other ones. It will look at the first 5 there, and it will say, right, this token is the statistically likely answer to come next. In order to predict the red, it takes all of the yellow, and it takes the green, and then it predicts the red. And this is how an LLM operates. There is a level 6 to this after. We go right into transformer architecture, but I'm going to save the audience from that for now. But the point is, this is how they predict the next word. And I hate when people say that because it kind of dismisses the capabilities of them. Truthfully be told, if you have an analyst, let's say, and you need, I don't know, a call summarized. So what you can do, you might send them an email and you might say, hey, could you please summarize this transcript for me? Make sure you don't include any names, and could you summarize the key points in bullet points form? And then you say, here is the transcript, and you'll copy and paste the transcript. What's their reply going to be? Well, it's probably going to be something like, here is the summary, colon, and then whatever the summary is. So by just predicting the next word, we are giving it context at the beginning, and then it's using all of these features that we've mentioned to kind of give you an answer. Like if I gave the context of the best team that wears red based in London is, I don't know London football teams that well, so this example might fall down, but I believe there's only one, Arsenal. Well, we've given it enough context to narrow down its answer. I'm going to stray away from football now. I try and avoid those examples where I can because I don't know that much about it, to be honest. But anyways, that's it. That is LLMs. That is our deep dive. So that is the most complicated thing I am going to show you today. We do have a lot more content. We're going to talk through how we scale this up, what that looks like, and then if we got time, I've even got some image generation stuff at the end. But I do want to just answer a question. We've had one in. So Derek asked, given the effort required to embed words into code and apply rules about language, such as word order and meaning, and statistical likelihood of different words appearing next to or close to each other in a text, doesn't that make an LLM's development very specific to one language, i.e. English, since AI development would be most advanced in English-speaking countries, and the general pervasiveness of English-speaking cultures worldwide? What effects would this have? That's a great observation, and you're right. So first of all, English is the best, I'm going to say air quotes, language in terms of when an LLM is trained, because you're right, most of the LLMs started off being trained on English. Most of the data on the internet is on English. I will caveat that by saying Chinese models are quite advanced. Chinese language tokenization is also kind of interesting because one character can actually be multiple tokens rather than us having 4 characters in one token. It's kind of the inverse, but that's a separate conversation. There are ways of dealing with that though. So what you'll find is you can get LLMs to operate in some different languages. Some of them have tokenizers which include different languages. Some of them might have translation as a sort of front end and back end service. It really depends on the implementation, but you can equate words together. So in that pre-training bit, you can equate café, which is coffee in French, with coffee, and also café, which is a cafe, with a cafe in English and French. So you can still, and actually you find this in embedding models, you can see embedding models where they map different languages against each other. We had a funny issue in production with that actually, which I might come on to. And then the other question, Kat has asked, what methods have you seen successfully or not to reduce or remove hallucinations? We will come on to that. We do talk about that in this part. So what is the journey to scale? So most organizations, they will start off somewhere with demos and proof of concepts, but I want to be very clear about a proof of concept. To me, a proof of concept means that you have done some form of a scaling plan. We did the demo for our first service back in April last year in 4 days, and it took 4 months to scale it. And that was because it was very easy to do what we did in the context length of an LLM. But when you break it out at scale, you needed to be a bit clever with how you approached it. So not every organization, but a lot of organizations are still down there. I always say, somebody once said, we've got 100 demos and 100 use cases in our thoughts. And I said, you've got 99 ways to waste your time. Um, Sometimes the best thing is to just get started. And that's where GenAI Labs kind of come in. So it's a bit more of a beyond experimentation, but before production. You want to make sure that you can build what you can. You want to integrate with teams because the answer isn't always like a data scientist. Like this is a software engineering problem. At scale, about 95% of Gen AI is not Gen AI, and we'll come on to that. And then finally, you've got that enterprise level Gen AI where you've got your data flywheel, you've got your ML ops, you've got like the whole organization along with you. I always say a Gen AI build is the final boss of an organization because everybody wants it to succeed. Everybody knows they need to care, but not everybody knows how to care. And what I mean by that is your governance board absolutely knows that they have to be on top of this because of all the regulation and everything going on. But at the same time, they don't know what that means. Like you can go to your data security people and you can say, yeah, we've got a vector database which stores embeddings and blah, 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 blah. And they'll be like, okay, I don't know what any of that means. But what you can say is, you can say an embedding is a representation of a data point. And that data is stored in a vector database, which is just another kind of database, by the way. And it's stored in this cloud region under these security parts. And all of a sudden, you can start to apply frameworks. So you take the principle of least privilege and you say that if the embedding has the same classification of the data point that it is representing, so if it's an embedding of a name, that's PII. And all of a sudden, we're talking about PII on a database in EU East 1. And all of a sudden, the security teams start to know what that means. So that's how we go into like the organization. That's why it's the final boss of the organization. And really, the data scientists are kind of at the key of all of that. So there's a few different arguments. I'm not going to talk about the next couple of slides. I'll talk about these, but there's a big slide of text. We'll share these out, and I do want to talk about the build, buy, boost argument, which is, do you build your own LLM? No, you don't. Do you buy access to an LLM, as in through an API service? Probably the right answer. Or do you boost, i.e., fine tune an open source model that currently exists? That's a good. That's also a good attempt. As part of my thesis back in 2021, we spent a lot of time training a customer service chatbot on IMDb movie lines. There might be some people in the audience that are screaming at that, but don't worry. So this is my crib sheet. This is all the hyperparameters. This is all the stuff we did. You can see there, the fourth and fifth last column, the epochs. Like it was a hefty amount of work. It did this a lot. That was me running out of GPU memory. And it was terrible. It was absolutely terrible. So I asked it questions. Remember, customer service chatbot for a holiday company. I said, hello. I said, hello, Thomas. How are you feeling? Okay. But then never told you my name was Thomas. Can I book a holiday in a long time? Tell me more. I'm sorry. About what? I don't know. I'm just trying to get some rest. I agree. And I wanted to stress the very first bot, the very first reply was this, and I'm not even kidding you. I did also put this in my thesis. I'm not going to read that one out. It's quite funny though, isn't it? That was the very first thing it said to me. We'll come on. This slide will be shared around, but it kind of talks about the pros and cons of each build, buy, boost, whatever. Even build. One thing to point out. So Bloomberg built their own model based on their own financial data, which is their own company asset. They did that. I think they spent about $20 million doing it. and they tested it against GPT-4, which is a generalist model, and it was worse than GPT-4. So usually the general models are better, but not always. Okay, so we've done that. We've talked about why an organization might want to get to the top. We've talked about how they might do it. But what is production when we talk about Gen AI? And actually, this is what I mean by it just fitting into regular software development. So this is the SDLC, the software development lifecycle graph. You start off by planning what you're doing, you code it, you do some code, you do the build. Code and build are different. Build is actually deploying it. Sorry, not deploying it, getting it in a Docker image or in a container or the architecture that will serve it to wherever it needs to go. You've got your test steps, you've got deploy, and you've got production monitor. And this should form a cycle. You should have a CI/CD process, continuous integration, continuous development. I might be wrong with that. It's either development or deployment. And basically that is how you keep your things up to date. Like all of this should be automated as far as possible so that when you have a new release, it's sense checking it and coming back to it and saying, yes, this is good or it's not. These are some actions there. Infrastructure as code and various other parts. I'm not going to take you through this because this is not anything related to Gen AI. But the next question is, how does this change with regard to Gen AI? So I would say the biggest parts that change, and I want to stress this is when you're building a Gen AI application. And even that, when people say they're building a Gen AI application, you're not building a Gen AI application. You're building an application which has Gen AI features. That's an important distinction. So planning changes the most. You have to do a lot more here. And that's because it's right now, a lot of companies and people and organizations don't really understand what it means at scale. We don't have the adjusted frameworks yet, but we are getting there. Build is a little bit different, where you deploy your hardware. Test and production slash monitor, I'm going to take as the same thing. They change a lot as well, and we'll talk about how I test some of my services in a little bit. So the biggest thing is use case. That can drive things like what prompts you need. That will also help drive things like architecture requirements. I'm not saying that your prompts lead to architecture requirements, but it's part of the picture. On-premise or cloud-based. This is interesting because this is, do you work in a regulated industry where you need to point at the box in your basement for the regulator and say, yes, everything happens there? Well, cool. You have a hardware cost. It costs you X amount of dollars per hour to run, and it costs you X amount of dollars to buy. But you could just use a cloud service, which is consumption based and linear scaling based on the number of tokens. So if you have 50,000 and you have 5,000, it's a pretty good estimate to say that it'll cost you 10 times as much. Not always, but general rule. But hang on a minute. What about if you don't want to do on-demand cost, but you want to have it in a box in your basement? I'm sorry, you can't. But you can also have the cloud consumption cost model if you can sacrifice that. So there's a lot of trade-off you can kind of see, and you want to plan all of that in advance. You don't want to be doing it while you're developing. The biggest component here is the vector database and also the LLM endpoints. Like, how do you actually provide them in whatever infrastructure, AWS, Bedrock, Azure, OpenAI, whatever it is. So testing, you've got two types of tests. You've got the quality of the output. So I'm going to call that as accuracy. And you've also got RAI, so responsible AI. And this is a bit of a general topic, but I think the ethics of AI and the ethics of generative AI, they are a lot of lessons from the first can be applied in the second, but there are also things in responsible AI about how you handle data. So, for instance, if you're using an endpoint like a cloud service, you don't want to be sending customer names to it. You don't want to send Ross or Adam or Paul. What you might want to do is replace that before you send it to this service. You might want to replace Ross or any other customer name with the tag customer names. Um, Other point here. Sorry, I noticed somebody has your hand up. Just a wee reminder, if you could pop your questions in the chat, we'll answer them there. And I am going to come on to the one that I see there. You've also got runtime QA, which is like, how do you do this in a way that doesn't require a human in a loop? That's a little bit further down. Robin's asked, how do you evaluate reliability and consistency? Equations should be reversible. So if you start with queen and subtract woman and then add man, you should end up with king. Similarly, the order of addition and subtraction shouldn't matter, but does it? And if you ask the same question multiple times, the same system shouldn't give different answers unless there is a change in information from the interaction. That is a good point. I realize that you're talking about the king, queen, man example. But I'm going to talk about that in the sense of how we audit this. So the first thing you need to get over your head is, in your head is that it is inherently a black box. Everything you've said there, Robin, is true. You can set temperature to 0, which makes the model deterministic in a way, but at the same time, it's very hard for people to explain why it actually gave you this answer, why it came up with king is the next token and such. And that's why you have to kind of take a black box approach. So what I mean by that is, um, we'll come back to we'll come back to this architecture point because it's kind of interesting. But I talk about call summarization a lot. Call summarization is one of the simplest use cases. You give me a transcript, I give you a summary. We know it's accurate. We know that it's quick. We know that it's cheap. It does it in 2 seconds. And the reason I can say all of that is because that's what the testing standards has held it to. Obviously, there's the engineering challenge. Like I say transcript, but people phone. It's voice data. How do you get real-time speech to text into transcript as a variable? Well, you have to answer on it. So just to come to your question, Robin, the way that we do this is by taking a black box approach. So we have our transcript. It goes through the process, which we call interaction summarization, and it gives us a summary. The way we test this is by having a known reference data set. We call it the golden source. This is 500 human labeled and created transcripts with not one human, I should say. We actually have about 10 or 15 people that we spread work across because you want a diverse sort of write up. And then we've got the appropriate summaries with them. And those are transcripts and summary pairs that we have labeled by humans, and we know that they are correct, and we accept those summaries as accurate in the context of those. And what we do is whenever we release this service as a new update, we run checks on those. So we take the input, which is transcript, we put it through our candidate service, we get an answer out at the other end of what the generate summary is, and we compare it. We do a random sample plus cosine similarity. There's a few other checks as well, and that gives us a pass fail. So that's how we measure accuracy in the sense of this. The other thing to point out is this is really interesting in the context of call summarization. Take this to a chatbot, it's useless. It doesn't mean anything. But that's the thing about auditing these on a use case level. You kind of have to design for it. And that's why the data scientist is important, because most of the tools which you'll use are your traditional NLP techniques, natural language processing. Even within this, like I've used cosine similarity, that's very good at getting semantic similarity. But if I was working with a legal client, it's very, very, very important to recognize that in the legal world, specific words mean very certain things. You don't want to turn the banking regulations of 2020 into Banking Act 2020, because that might be a completely different thing. So all of a sudden, you need to be checking for the correct word. So you're thinking something more like n-gram analysis. Again, it all really depends on the context in which you're working. It's really hard right now to generalize this stuff. You can generalize at a use case level, sort of like summarization or RAG architecture, but the point is it's quite a difficult problem right now. That's what that looks like in an architecture diagram, by the way. There's obviously the software engineering part past it. So I would say that yes, there's the theory, this bit, but there's also what does this actually look like in practice? And this is the high level diagram. There are the code and logic and everything else underneath this, like how is authentication handled and all that sort of fun stuff. So this is one example. I do want to just jump back very quickly on the slides. I glossed over something. This is what's called a RAG architecture. Very simply, RAG is how you use more relevant data to make the LLM's response better. Obviously, they're trained on a data set. That data set has a cutoff period. Or you might have company sensitive information in your internal part. You need a chatbot, for instance, that can answer customer queries based on your existing internal knowledge base. So what you can do, you can take the human's question. So in this case, I'm planning a 5-year-old's birthday party. You get the vector of that. You do a vector search in your store. You find the best answer to that. And when you create your prompt looks something like the initial part, which is here is the user's question, and then a set of instructions. And then here is some additional context which might help you answer. And that context in your input to the LLM will give it a better answer. At least that's the theory and that's the practice. So this is it in terms of high level architecture. This is it when you add it to production, all those gray boxes. You will notice that pretty much all of those have nothing to do with Gemini. You could argue prompt template is, but I would also argue that that's just storage of a known variable. That's the point. most of Gen AI at scale is not Gen AI. You build the prompt, you do some other stuff. I will admit it can take up a lot of it, but it's not all of it. So just moving quickly on, we've got 10 minutes left, 15 minutes left, and then 5 for questions to answer. But what does this all mean? It means this. So you started off, you have a bunch of sad engineers, and they have a pile of complexity, and then they build apps from that. And what people thought AI will do, or think AI will do, it will take happy non-engineers, and the AI will magic away that hidden pile of complexity. What actually happened is those sad engineers need to learn new complexity, a new pile. There's even sadder engineers sitting over the old pile, and then you build the apps. So it's not coming for your job yet, is my main takeaway here, at least for now. I'm just going to scroll quickly through the questions. I'm going to leave those questions for the end. I think I'm very happy to say that we've maybe answered your question, Robin. But if you feel like there's some points that you'd still like to pick up, please do drop another one in the chat. The rest of them we'll come back to at the end. I do just very quickly want to take you through image models, very, very quickly. So what is an image model? It's a different type of generative AI. It's something called a general adversarial network in most cases, not all cases. So an image model is a type of Gen AI called a general adversarial network. They have two parts. They have a generator, which generates data, and they have a discriminator. The discriminator is trying to distinguish between the real data and the generated fake data. It penalizes the generator for that, and there's a cycle to it. So what happens is the generator starts off with basically noise. Looks a little bit like this. The discriminator looks at the generated data and compares it to the real data point there and says, right, that generated data is fake. Training continues to progress, and you get that first picture there. So it's trying to draw a $100 bill. It's drawn a 10 with a sad face on it, but it keeps going and going. And that training cycle ends up with it looking like real data until eventually the discriminator is the one who is losing, for lack of a better term. And that's how most image models work. It's really that simple. It is interesting though. There are different models. So you've got Midjourney. I'm going to group these together. I'm not going to talk through them, but I am going to point out one of them, which is a bit interesting. So these are the three ones that most people might have heard of. You've got DALL-E 3, you've got various other ones. You've also got Adobe Firefly, which is something that I want to point out. And this one's specifically interesting. The reason it is interesting is because when you look at the training data sets for most of these models, most of them have been trained on copyrighted data. There's a lot of court cases up about that. Keep an eye on the Warner Brothers case in the US. That's a really important one. But Adobe Firefly is specifically made for creatives. And the reason it's different is because it has not been trained on any sort of copyright data. It's all Creative Commons data. This is really interesting. It's really good. It's quite a strong thing for creatives because they can use that generative model and know that there is no risk to them having a lawsuit against them, for instance, in the future. So here's some outputs from them. We have prompted them a little bit different. Each of them requires sort of different prompting techniques. You will see that there's Midjourney, there's DALL-E, there's Adobe Firefly. All of these are close-up portraits of a young woman, high resolution, and so on. I'm just going to go through the next few pages because I want to make sure we get to the questions. This is a young man in an urban setting. Midjourney is quite interesting. It usually stylizes these things a lot. You can see how they all do different things, how they all have different styles. Adobe Firefly, you might notice one thing there. It says a portrait of a young man in an urban setting with a comfortable stance, sharp, gritty realism, and gritty realism and sharp textures of the cityscape behind him. That is a blurred photo. It's not sharp. And you could imagine that the Creative Commons dataset has a lot of sort of portrait pictures, and most of those will probably have some sort of focus on the main part of the photo, and then the backing blurred. Maybe that's a feature of how they were trained. I don't know. Just a theory. And then here's a black and white photography style portrait of an older man. I find it funny how Firefly does. Well, we didn't say older man, but we did try and get it to that by describing it. You'll find that a lot of these models, you can't ask them specific things. So, like if you ask them to generate a photo of Barack Obama, they won't. But you can describe the person in either features or in terms of who they are, and you can get around it because it's just a word filter usually. How do you use these image models? Well, there's a few different ones. You've got text to image, which is done by attaching text tokens to those images when you're doing your GAN training. This is the most simple one. Most people will have heard or maybe even used this themselves. Um, you've got image to image translation. So this is an example of style transfer. This is Van Gogh. Again, most of those services now will block specific painters, but you can kind of talk around it if you know enough about the painter. You can give a description of their style. Um, image to image translation. So these are sketches. You can get it to build out a sketch. I don't think most of these look like realistic people, but there is a lot to be said, again, in terms of the image training data. So one thing I want to point out, in Australia, there was, I think it was a politician who basically was a photo of her was published in a magazine and it looked nothing like her. And they had used generative AI to make an image or part of an image about her. And unfortunately, it's the case that most generative AI models have a lot of stylized images of women in them, obviously, ones where the original image was photoshopped or cropped or blurred or whatever. And that led to some of these models not having accurate representations of females. It's an unfortunate side effect of how training data is handled, and it's a great lesson in why training data is important. It's the secret sauce of all of these models. They're not really doing much different in how they train compared to one another. Small things here or there. Their secrets are their training data, and it's why they don't want to publish training data. Like if OpenAI, they will not publish their training data set because they might get sued for it, but also because they kind of give away their secret to all their competitors at that point. I like my memes. We're almost there. So generative AI that draws a picture from word prompts, that makes me a bit of a human artist, doesn't it? Well, um, this was something we did with Nationwide. This was just a bit of fun. We were just generating images for them. Bottom left one there is Nationwide Bank. Now, I know that some of you are thinking it's Nationwide Building Society. I'm going to get onto that in a second. On the right, generate an image that describes Nationwide Bank in the UK in the style of an 18th century painter. Ignore the one on the right. It's a cool photo. Doesn't really mean anything. The words are a bit messed up. The one on the left's pretty good though, isn't it? I mean, even the logo is. Wait, hang on a minute. Ah, did you spot what was wrong? Well, from a distance it looks passable. Up close, yeah, not so much. And actually, this is, if you go back to how they were trained, the general adversarial network, what's happening is it's getting there until it's good enough, until it can fool the discriminator. That's why things like hands on generated images and text are quite difficult because it's very, very fine detailed. Um, yeah, from a distance it looks okay, but you get up close, not so much. Usually most text is added in post-processing, by the way, and hand models, there are specific generative models that actually go in and correct hands. I found that fact really funny. And the final part, this is the last part of the presentation. You might be wondering, why didn't I call it Nationwide Building Society? And actually, when I did that, this is what I got. This is a really cool image, by the way. But what it did was it interpreted building society as quite literally building society. To me, this sort of hologram, let's call it, looks like a logo or an ideal sort of thing for building the next future society. Like you've got Bitcoin up there, you've got a few different things, but that's the point. Building society, as in the literal sense that we all know, versus building society. Yeah, I found it interesting. So thank you. That's the end of the presentation, but I do want to note we've got 6 minutes left. I'm going to answer the questions in terms of the most recent order they came in. I will come to them, and if there are any questions that are sort of still lingering, we will try and answer them in the community. But just to give it a start, so Anna Moss asked, how much could it cost and how long can it take to produce an AI agent, any random, based on a common LLM for a UK client on average? Oh, my question is, what's it going to do? Um, how many people is it going to speak to? How long do you expect those chats to be? Because you get charged per generation. I'll come on to that in a second. It's really hard to give an average there, and the reason is because it all depends on volume. It is linear scaling in terms of how volume is approached, but I will caveat that by saying it with chat use cases specifically, it does depend on one particular part, and that's how many messages there are. So when I send my first message, I get charged for the input of my message and then the generated message. Let's call those both length of one. So I get one input cost, one output cost. When I generate the next message, so I've come back and I've given a reply, I have to put in the context for the generation there, the first message, the first reply, and then my second message. And then I get the second reply as the generation. So that's 3 input, 1 output. But you still get charged for the first 1 and 1. And then when you go up to the third utterance, like iteration, it's uh, first generation, sorry, first user message, first generated, second user message, second generated, third user generate input, 5 input, and then you get charged for the 3. So that's actually a exponential scaling of cost, which is why most solutions will only allow like the most recent 10 or 5 messages or whatever. So I'm afraid I can't really give a concrete answer for that. But you're not talking like millions and millions. Like people do this for 100K or less, some of them even less. But again, it does depend. I tried programming by Python with generate a key from ChatGPT. Can you please give us some advice on how to do that well, please? When it comes to code generation, I would use motivation helps for these models. So what I mean by that is in the system prompt, try and set something. Say you are a 10x. You know how people say, "Oh, if you ask it to tip and stuff, it'll work better." That is actually true. We don't know why that works. There's some research about it, but like we don't really know why. Um, and to be fair, what I do is I have a prompt. I always say, "You're a Python engineer, 10x." You always give full code. You will discuss. Like I could try and describe the person that I would want to have work with me on it. So that would be my advice is if you're trying to get ChatGPT to do things, try and get a good system prompt, try and tell it what it is, it's a good engineer, etc. The other thing is look at trying the advanced models, so GPT-4, GPT-4o, they tend to be better. But that's my advice there. Do you have any recommended reading materials for newbies in LLM? Um, it depends on how technical you are already. I mean, you can never really go wrong with the paper attention is all you need. But that is kind of complicated. Um, to be honest, I would say there's a guide by Anthropic, and I'll try and get that link shared around. It's for their Claude 3 model. It does a good job of explaining how Claude works, and it also gives you some prompt engineering input and how you can best prompt engineer for Claude. That's quite a good one. If I don't send that round, Adam or Paul, please do remind me. But we'll try and get that round. That's from a technical angle, that's probably where you want to go. But if you're looking for the academic part, I would go attention is all you need. But there's a lot to read there, so you can never go wrong with a quick Google either.
There's
Um,
probably some stuff just on that, Ross, as well in the community already. So there's obviously a forum within the Data Lab community that members could come on and ask that question. So again, if you're not already a member of the community, please use the QR code down in the bottom right corner. Within there are forums that you can ask other members of the community alongside Ross. Their reading materials that they've used to kind of upskill on LLMs. So that's my input on that one as well.
yeah. Um, do you use RAG architecture to deal with drift in LLMs? You can, but there are better ways of doing it, is my impression. And so it's not really a direct answer. I do appreciate this, but it sort of depends on what you're trying to do. So in RAG, you are obviously trying to answer a user's question. There are various things that you can do. So you can do cosine similarity of the generated answer back against the source document. You can do some various other checks. There's also a thing called LLM as judge, which I don't really agree with because you're basically asking a more advanced LLM to mark that LLM. You basically say, here's the question, here's the answer. Does this make sense? Yay or nay? And then you deal with it that way. There is also some research. I won't pretend to be too far into the dealing with drift question, but there is some research on how we can correct that at sort of a training level. Um, but usually accuracy is how I would deal with it by checking that an answer is accurate, whether that's at build or whether that is in real time, like checking a chat session, for instance. Um, but that you can use parts of it to deal with it, is my answer there. Robin Hill, sort of follow up, as you might have guessed. I'm okay to go on, by the way. I don't mind staying a couple more.
Just mindful, we probably need to start wrapping things up now. But what we will do, Robin and Kenji, we can see your questions have been asked here as well. What we'll do is Ross is in the community, so please make sure you'll be able to find him as a member in that community, and you can go ahead and ask him these questions again. I'm sure, Ross, you wouldn't mind answering those, certainly
Yeah.
from kind of an in-mail from the community side of things. Um, just in the essence of time and to kind of draw things to a conclusion, from my side of things, I just wanted to thank you, Ross, for coming and joining us today. We've certainly enjoyed your conversation with us. Really, really insightful content here. So hopefully, and I'm just picking up the general vibe from our community members here, this seems to have gone down really well. And certainly it seems to be a topic that people are really wanting to learn about. So thank you very much for doing that for us.
Yeah, and thank you for having me as well.
Oh, no, no problem at all. And again, thanks for the partnership with Accenture for bringing forward this type of content. It's phenomenal to get this out there into the community. A couple of things from my side as well, just as we wrap up. So obviously, Data Lab runs a community itself. This is some of our activities that we're running. We continue to run these sessions monthly and often cover really interesting topics such as this. So from our side, we would really welcome you to come and join us again for other types of community events that we run. We also run some in person as well, so we would encourage you to come and do that. So I have got two upcoming events that I just wanted to signpost people to just before we wrap up. So we've got a Data Lab community meetup. This is an in-person meetup, but we do also have an online function to it. And for people who are close to Edinburgh, it's going to be held at the Bayes Centre. This one is around healthcare and around how data and AI is being impactful in this space of health. That is on the 30th of May and runs from 5:30 till 7:30. So please, if you're around the area or you want to join us online, please go ahead and do that. We've also got a Woman in Data and AI meetup again. This is going to be hosted on the 18th of June, just to double check that a date, but yes, 18th of June. And again, that's running from 5:30 till 7:30 at the Bayes Centre in Edinburgh again. So for either of these events, please do go ahead and sign up for them. Please make sure you advocate and tell others who you think might be useful to come along to these events. We would love to see you here and joining us. I can see my colleague Paul is just dropping the links in to these events in the chat function, so that's fantastic. So thank you very much for that. All that's left to say is thank you for our audience members for joining us today as well. We appreciate you giving us your time on a Friday afternoon, particularly around lunchtime. Very much welcome that. And thank you for the engagement across the board. If you found today's content useful, please do go ahead and tell other members of your friends, your family, your colleagues about the exciting activities that you've been able to participate in here today. And we look forward to seeing you in the very near future. So on a final goodbye from me, please go ahead and enjoy your weekend. And we look forward to seeing you at our next event. Thank you very much.